All right, in this podcast, we're going to talk about different types of equations. There are several different types of equations that you're going to have to deal with. The first is the molecular equation. The molecular equation is what you're used to. You're used to writing the equation, and then we assign the states of matter, which we'll get to in just a second. So this is what we're used to writing. The complete ionic equation is basically we're writing what would happen if we threw this mixture, this reaction, into an aqueous environment, into water. So if something were going to break into its ions in water, like ionic substances breaking back into their component ions, then that's where we're going to be writing this. And then the net ionic equation is when you take out all the spectator ions, or the ions that appear on both sides of the equation, and you get just what's really happening in the equation, what's really changing in that environment. All right, so molecular equations we're not going to worry about because you already know how to do those. Those are the regular equations we've been doing. Ionic equations are when you basically break it into its component ions. So you had lead nitrate, parentheses 2. So we broke that back apart into lead 2 plus and 2 nitrates minus, okay? Same thing for potassium iodide. And then the solids stayed together. And then again, another ionic breaks apart. So we're going to show everything as it would appear in water broken apart if it was ionic. Then you cross off all the spectator ions, and that gets you to the net ionic equation. So you cross out the things, let's see if we can erase them, okay, that are on the same. So we got 2NO3, 2K, 2K, 2NO3. Okay, so those all get covered up. But to be able to do all of this, you need to be able to tell what the state of matter is for each substance in your reaction. If you look at the periodic table in my classroom, the liquids are going to be blue. That's going to be bromine and mercury. Gases are red, so that's hydrogen, nitrogen, oxygen, fluorine, chlorine. And then the rest of them you kind of have to memorize. So carbon dioxide, sulfur dioxide, nitrogen monoxide, nitrogen dioxide, NH3, H2S, and HCN. So you need to memorize those last couple. And then solids are going to be any element that's just black on the periodic table, or an ionic compound that doesn't dissolve in water. That'd be based on our solubility rules, which we'll get to in a little bit. And most covalent compounds fall into this category as well as a solid when dissolved in water. Aqueous means a solid that completely dissociates in water. So basically that's going to be your ionic substances, and that's also going to be your strong acids or strong electrolytes. Okay, so if it's just a single element, you're looking at the periodic table. If it's a compound, we're going to have to look at our solubility rules. Okay, so here's the periodic table. Red represents the gases, and this is just if they're by themselves. Black is solid. And then the two blue ones are going to be your liquids, okay? The other couple of gases here you have to kind of memorize, okay? And you're going to have to get some feel of the solubility rules. So let's go ahead and skip ahead to the solubility rules. All right, the solubility rules are only good for ionic compounds. So ionic compound is a metal and a nonmetal. So if you have a metal and a nonmetal, you want to worry about the solubility rules to determine if it's going to dissolve in water or not. Okay, there are 6 simple rules, and there are some exceptions to those rules, and you definitely need to know the rules, and you need to know the common exceptions. Okay, all right, so everything that is in the first column of the periodic table are the alkali metals, and ammonium ion, which is NH4 plus. Those are all going to be soluble no matter what. Acetates, nitrates, chlorites, and chlorates. So that's going to be looking at the end of your compound, okay? The back of the compound. If it's got an NO3, a C2H3O2, a ClO3, or excuse me, a ClO2 or a ClO3, then you're going to be calling this soluble. Soluble means it's aqueous, which is AQ, okay? If it is a compound that just has a halogen, halogens are group 17 in the periodic table, then it's going to be soluble. There are some exceptions, so fluorine will not dissolve. It'll be a solid in aqueous solution when you're talking about it being bonded with calcium, strontium, barium, lead, and magnesium. Okay? Now, if silver, mercury, or lead are bonded to chlorine, bromine, or iodine, those are also exceptions, which means those will be solids as well. I don't think it's that important that you remember all these little exceptions for the halogens necessarily. They're not that common. All right, sulfates. Sulfates are always going to be soluble. Sulfates means SO4 is on the back of the element. Exceptions to that are barium, strontium, calcium, lead, silver, and mercury. I think you probably need to know the exceptions for that one. All right, now these down here, these last two rules tell us the insolubles, or the ones that are solids. Carbonates, which are going to be CO3 on the end of a compound. Hydroxides, which are OHs. Oxides, which are O. Silicates, which are SO3 or SiO3s. Sulfites, SO3s. Oxalates, C2O4s. Chromates, Cr, O4 and Cr2O7. And phosphates, which would be PO4. These are all insoluble. So if you have any of those things on the end, it is insoluble unless it's got a group 1 element or ammonium on the front of it. Okay? So, and that brings us back to our first rule. Sulfides, which are S, are also insoluble unless calcium, barium, strontium, magnesium, sodium, potassium, and ammonium. So it's probably important to realize that it's most of the first and second column elements with a sulfide would be an exception. So that's going to get you your rules for your ionic compounds. Now let's go look at this flow chart and try to make sense of it. It will help us, or help you, to try to determine what you need to do with an ionic equation. All right, basically this flow chart will help you try to determine how you're going to, when you look at an equation, how you know if something's going to be broken to its component ions or it stays together. Okay? There are basically two ways to look at this. If it's an acid or a base, okay, then you have to evaluate if it's weak or strong. Okay? If it is a strong acid or base, it means it breaks completely. It dissociates completely. That's what strong means, 100% dissociation. If it's weak, we're going to leave it together because we know that that's a equilibrium problem, right? Okay, so very small dissociation. All right, now most things we deal with are not going to be acids and bases, so we're going to be going this way. Then we have to look and see if it's ionic or covalent. Molecular means covalent. Ionic is a metal and a nonmetal. Covalence when you just have nonmetals. Okay? Covalents do not dissolve in water, so you're just going to keep them together, write them as a solid or a gas, whichever they appear. And ionics, you have to determine if they dissolve in water based on the solubility rules, which we just looked at. Okay? So if it's soluble, or AQ, then you break it into component ions. Okay? All right, when we're writing these ionic equations, we're trying to identify a precipitation reaction if it's occurring, which is basically if there's a insoluble product, okay? And basically when something is insoluble, that means that it doesn't dissolve very good in water, and water molecules are not able to overcome the attraction between the ions to break them back into component ions. Okay, here's a really good example. Okay, so you have Ki and PbNO3 parentheses 2. These are both AQ, so they would break up completely. And then we have a double replacement reaction. So lead and potassium swap places, you get PbI2 as a product and KNO3 as a product. Okay, so let's try to look at this equation and write out the net ionic and complete ionic equation for it, okay? All right, we're not dealing with any acids or bases here, and we know that AQs are going to break up completely, so we're going to get a Ki breaking up into K plus and I minus. And then here again, lead nitrate is soluble, so we're going to get Pb2 plus and NO3 minus. Now there are two of those, okay, from here. And that makes this is solid, so it's not going to break apart, so we're just going to leave it together. And then again an AQ, so it's going to be K plus NO3 minus. Now it really helps if you have the sucker balanced initially, which we did not. So let's go ahead and balance it. So let's see, put a 2 there and a 2 there, okay? And let's go ahead and just throw all these balance things in. It'll help a lot in a second when we go to canceling. Okay, so there's the complete ionic equation. And then you cancel things that are like on both sides. So I got 2 K pluses on both sides. Let's see, don't have I minus on that side, don't have PB, but I do have NO3 minus, 2 of them on both sides. So this is our overall equation. So you get the 2I minus and your PB2 plus, and that makes PbI2. So that's really what's happening in this reaction, and you're forming this pretty yellow precipitate here. Okay? Precipitate, yay! Okay, so that's what you're trying to do. You're trying to identify the precipitant when you write these complete ionic and then net ionic equation. All right, and to end, I thought I'd give you a list of all of the rules for writing ionic equations here. So first you want to write the balanced molecular equation. Remember the molecular equations, what you're used to, so just the balanced chemical equation. Then you take all the electrolytes and you break them down. So that's going to be your ionic substances that are AQ and all those things. Now you cannot break down solid, gas, or water. And then you're going to cross out everything that's the same on both sides. Those are your spectator ions. And what's left gives you your net ionic equation. Okay? So those are the steps in order.